All right, so this is the first in a lot of lessons that will look into the ideas of complex numbers, and in this lesson, the idea of the imaginary number, the imaginary unit. And so let me just get straight into it. The imaginary unit we can start to work with when we look at the quadratic formula. And this part here, the quadratic formula, recall, is called the discriminant. And most of the time, until now, when that number is negative, we would say the quadratic expression doesn't have any roots, or no real roots, we'd say. Or if we visualize it as a graph, we'd say that it doesn't cross the x-axis, which is correct. However, we want to go a little further now and say if that's a negative, that discriminant is negative, well then we say it does have actually roots. They're not real roots. They're complex roots. So there's still no x-intercepts, but it does have two roots and they're complex. And they'll involve this value I, the number I. And by definition, I is the square root of -1. And we'll see that a lot. We call that the imaginary unit. Therefore, if you take I and square it, you get just -1. Which, if we think about any square root, if you just pick, I don't know, the square root of 17, if you square that, you get just 17. And so if I is the square root of -1 and you square that, you get just -1. And that property we'll see a lot. So let's start by looking at the quadratic formula and find the roots of this, which will have roots that are not real. And so until now, we would say there's no solutions or no real roots. But there are complex roots we'll see. So using the quadratic formula, x equals -b, or in this case, -6, plus or minus the square root of b squared, which is 36, minus 4 times a, which is 1 times c, which is 25. All divided by 2 times a, so just 2. So in this case, we get -6 plus or minus the square root. And all of this here, the discriminant, comes to -64. So if we're only dealing with real numbers, we kind of usually would stop here and say there's no solutions or no x-intercepts or whatever. However, we want to start looking beyond just real numbers. And it's actually not too difficult to deal with. This root -64, I want to get the value of I out of it, which I can do quite quickly. If I just essentially factor root -64 into root +64 and root -1. Because again, root 64 times root -1 does equal root -64. And this part here, that is by definition I. And so I can now write this as -6 plus or minus the square root of 64, which is 8, times the square root of -1, which is I, divided by 2. And at this point, all there's really left to do is to tidy this up a bit. Notice both the terms in the numerator are even, which means they can both be divided by 2. And so I can just write this as -3 plus or minus 4i. So this expression for my roots has two parts to it. -3 is what we call the real part of the expression, and the 4i is the imaginary part, especially there's 4 of these imaginary units. And because they're different types of numbers, we can never write this into a single term. We'll always have this pair of terms, the real and the imaginary part. All right, and so looking at this here, same idea, go to the quadratic formula, minus b, so -5, plus or minus the square root of b squared minus 4 times a times c, so a lot of negatives going on there, divided by 2a, so -2. And so at this point, my discriminant here should come to -7. All right, and again, we don't have to actually stop here because I can take that root -7 and I can write it as root +7 times root -1 over -2. There's my imaginary part. So I can now write this as -5 plus or minus root 7 times I, being careful that the I is not part of the radical, divided by -2. And while I'm essentially done, I do have a few extra negatives, more than I need. And so just notice the whole numerator is being divided by -2. When you divide by a negative, you just change the sign. So I can really write this as +5 plus or minus, because either way, that's going to be a plus or minus. Root 7 times I over +2. That's considered to be a bit simpler. And while you may be, one option instead of root 7i is to put the I first. That makes it more clear it's not in the radical. We usually put the I second. It doesn't really matter though, so I'll leave it like this. All right, so for this, I have an expression where I have a minus b plus 5i equals 8 plus ai. And I want to determine what these values of a and b are. Well, one thing to realize is that if I look at this, I have 5i on one side, and I have a times I on the other. And no other of these terms involve the imaginary unit, which means the a minus b and the 8 on the other side have nothing to do with the imaginary values. So I know that I have 5i on one side, I have a times I on the other, which means I can right away see that a must equal 5. Well, that's nice. There we go. And so similarly, if I look at the a minus b on one side and the 8 on the other, those are the terms that have only real values. There's no imaginary units there, which means I know those two must go together. And so that means I can also say that a minus b must equal 8. But keep in mind, I know that a is 5, and so I get 5 minus b equals 8, which means b must equal negative 3. Because again, the imaginary parts and the real parts are different number systems. They cannot be combined, and so this actually ends up being a pretty quick question, which kind of leads into this next part. I have two imaginary numbers, z1 and z2. z1 is 3 plus I, z2 is 2 minus I. And so all of this here is actually really quick and easy as long as we're familiar with what the notation is describing, I should say. And so for this, RE, that represents the real part of the number z1. And so, which in this case, if I look at z1, the real part is just the 3. And so I can write this as RE, real of z1. The real part of z1 is just the 3. And the real part of z2 is just the 2. That's it. And so all complex numbers have a real and an imaginary part. And so now these are looking at just the imaginary parts, which are the coefficients of the imaginary unit. And so the imaginary part of z1 is the coefficient of that plus I, so it's just the 1. And the imaginary part of z2 is the coefficient of the negative I, which is just the negative 1. All right, lastly, when you see an asterisk there in a superscript, that represents the conjugate, the complex conjugate of these values. And ideally, the word conjugate is familiar. It comes back from previous courses, and it's actually a pretty easy thing to work with as long as it sounds familiar. And so the complex conjugate of z1 is, the complex conjugate of 3 plus I is 3 minus I. And the complex conjugate of 2 minus I is 2 plus I, which if we're familiar with the word conjugate from previous courses, it doesn't take much explanation. So the complex conjugate, which is denoted with an asterisk, is going to be 3. Take away I, and the complex conjugate of z2 is going to be 2 plus I. All right, now the conjugate is quite useful when dealing with certain algebraic expressions that we want to work with. In this case, I want to go z1 divided by z2. And so if I want to divide these two values algebraically, I can do it rather quickly if I use the conjugate of the denominator of z2 in this case. And so first, z1 over z2. In this case, z1 was 3 plus I divided by z2. That was 2 minus I. So to evaluate this, I can do it quite quickly if I multiply this by the conjugate of the denominator, both in the top and the bottom. So the conjugate of 2 minus I is 2 plus I. So I just want to multiply the top and bottom, the numerator and the denominator, by 2 plus I. And we do similar things in previous courses when you rationalize the denominator of a radical expression, or in trigonometry, previous courses, we tend to use the conjugate to get to some of the identities. That's it. If I look at my numerator, I can just distribute these two binomials essentially. And so I get 3 times 2, that's just 6. I get 3 times I, which is 3I. I get I times 2, which is 2I. And I get I times I, which we saw before is -1. In my denominator, I could do that. Well, I'll definitely go 2 times 2, which is 4. However, keep in mind when dealing with conjugates and multiplying, essentially like a difference of squares here, the next two terms cancel each other out. I have 2 times I and minus I times 2. Those two cancel each other out. So all I really have to deal with at the end is minus I times positive I. Now we got to be careful here. I times I is -1, but it's minus I times positive I, so we're subtracting that. So really when I clean this up, in my numerator I have 6 minus 1, which is 5, plus I have 3I plus 2I, which is 5I. In my denominator I have 4 minus -1, which is 4 plus 1, which is 5. And this can definitely be simplified. Both my terms in the numerator are exactly 5, so if I divide everything by 5, I get just 1 plus I. It's actually quite a pleasant expression. That said, in this course, you are always expected to have access to a GDC, and on your own, I'm hoping you can quickly find, if you can just type this into your GDC, and again, all the GDCs we use in this course have some way of typing in the imaginary unit. If you just type in 3 plus I divided by 2 minus I, it should bring you straight to this. And so your GDC ends up being quite useful to take these rather mundane calculations and just speed them up, which is obviously the point of a calculator. All right, lastly, similar to a previous question, A and B are real numbers, and I have the expression on the left equaling the expression on the right. And what is A and B? So what I want to do first is distribute this. So again, 2 times A is 2A. 2 times BI is going to be 2BI. And then -3 times A, sorry, -3I times A is -3AI. Now keep in mind, I again is not a variable, it is the imaginary unit. And so while I don't have to write it last, I would, just to remind yourself it's not a variable, it is a different type of number, it is a square root of -1. Hence I'm putting it last. And finally, I have -3I times BI, which is -3BI squared. And I squared is -1. And so instead of writing like that, I'm just going to change this to plus 3b instead of subtracting a negative. All right, and keep in mind all of this equals 4 plus 7i. And so looking at what I've looked at before, if I look on the left-hand side, the 2a and the 3b, those have no imaginary parts, so they must connect to the number 4, which means I know that 2a plus 3b must equal 4. Similarly, the 2bi and the minus 3ai must equal 7i, which means I know that 2bi, actually I'll write these in alphabetical order. So I'll start with the -3ai plus 2bi must equal 7i. Which means if I look on my left-hand side, if I factor out the I, that means -3a plus 2b, all that times I. That means -3a plus 2b must equal 7. Which means if you look at these, I now have a system. I have an equation here, 2a plus 3b equals 4. On the other side, I could simplify this down to -3a plus 2b. That's a weird looking 2. -3a plus 2b equals 7. And I can now solve a rather simple linear system with 2 unknowns. You can do this algebraically. Ideally, you can just use your GDC, the simultaneous polynomial solver. However you do it, you should really quickly now get, because the hardest part should be done, so you should get to a equaling exactly -1 and b equaling exactly 2. And since we get such nice values, whether you solve it algebraically or not, should be fairly quick. The key part to this is realizing, again, when we have this mix of imaginary parts and real parts, they cannot ever be combined into a single term, and that's how I knew how I could break this up into two separate parts.